Hello. This is going to be some sort of discussion, informal discussion about random variables in a measure theoretic perspective and how we basically define random variables and maybe some motivational examples uh, and why this new tool is relevant in probability. So basically, one basic idea of measure theory is to look at algebra of sets. By algebra of sets, I mean you the same way you add numbers. Now you think of subsets, say here A and B. Now you want to add two sets to get another set, but what you're using is the union. So the union of two sets is some sort of addition, and the intersection of the sets. This goes for this is more like multiplication. Is a good exercise if you think of what would be like the zero, like number zero in numbers. What would be it in the case of sets, or what about number one? Number one is the number that if you multiply with anything, you get the same thing. Do we have anything like that? This is going to be a good uh, exercise. Now, I want to give an explicit examples how we create such an algebra of sets. So we have to pick a specific family of sets and then say you can now add anything that belongs to this family and get another set which is inside the same family after you do that operation. So in other words, here I'm taking a set A here, which is shown by a yellow color. Set A it's a vertical set, meaning that it is a union of vertical strips. And now if you take two sets which are vertical, like one of them, for example, is what you see here, and then you take the union of them, it is going to be vertical as well, right? So, and also if you do the intersection, so if you take two sets that are vertical and you take the intersection, it might be empty, which we still think of it as vertical, or uh, it should be vertical. There's no way you can take two vertical sets and using the two operation we had, intersection and union, uh, to create something that is not vertical. That would be impossible. So now, so in this sense, now this vertical subsets on the square shape, they define an algebra of subsets of a square. They're not all subsets, but they still have the operation union and intersection defined for them. Okay, so now there is now another additional extension that we're gonna need in measure theory. That's the concept of sigma algebra. We just talked about algebras, but there's a big difference between algebra and sigma algebra, and the difference is in sigma algebra we would like to add, or in our case take the union of an infinite family of sets and still belong to that family. So we, in the previous slides, we saw that, yeah, so you can take two sets and take union, you still be vertical. But actually, if you take infinitely many vertical sets and you take the union, it's going to be vertical as well. So we want this whole algebra to be closed under infinite operation. But by infinite, we mean countable infinite. You give me a countable family of elements of C star sigma algebra, and then you get another element. Okay. Now, if a subset belongs to the sigma algebra, we call that subset measurable. In the previous example, a vertical subset is a measurable subset. If you have a subset which is random shape, not vertical, we don't call that measurable in that example. So in general, you can define whatever you want as your algebra of subsets, and then whatever is that in that family, we call it measurable. Okay, measurable subset. Measure of that subset A. So every set has a measure. And if you think of this as like from probability perspective, for every set A, we want to know what is the probability of some sort of event happening, which described by A. Now we want that map that sends sets to measure like quantities, values. We want that to have some properties. We said P of A is a number. You can add numbers. So now we want, if you take two disjoint sets, so A and B, they don't have intersection. They're like A and B. And when you measure the set A union B, what you get is P of A plus P of B. So another way of writing this is that P of A, if this is disjoint union, B is P of A plus P of B. If they can have this intersection, then this would be less than equal. Okay, so this is what we mean by a measure. Now we want an additional property. We definitely want the empty set to have measure 0, and to be a probability measure, not just any measure, specifically to have a probability measure, we want the measure of entire space. Remember, this omega is like sort of the universe, and A is a subset of that omega. So the entire space, if you say what is the probability measure of the whole space, that should be 1. So that we'll have a way of assigning numbers, but that should satisfy these axioms. Okay, now we come to the definition of probability space. A probability space is a triple. You have 3 pieces of information. You have a universe of events, or you can think of this possible states of your system. And then you have a families of subsets of that omega. So any A in this family is actually a subset of omega, and everything in that C star algebra, sigma algebra, so this is one that we have, sigma algebra, everything in that sigma algebra is called a measurable set. Now then we also needed a probability measure. We just described that. If you put all these 3 pieces together, you get what is called a probability space. Okay, but now we have a probability space, but we don't have a random variable yet. How do we define a random variable? Remember from the previous slide, we had the omega, we had the sigma algebra, and we had the probability, but we are not assigning numbers yet to any event. Let's say you're interested in the temperature of your room. Now you take a state of the universe, or let's say an event in the probability space, and say, okay, for that particular state, what is the temperature in my room? Now, obviously, if this is the state of universe is something that you don't know exactly what is it, and it's some sort of probabilistic information, then the value that you get for the temperature of your room is going to be probabilistic as well. Okay. So now in a way you can think of you're labeling every event in omega uh, with a number, with a real number. Um, okay, so this is the way we label things. We might have some specific scaling, temperature in what scale, but that's all again assigning numbers to it. Okay, now when you think of a particular set of values, you ask the question, what is the probability of the temperature? Let's say temperature is a random variable and it's x. What is the probability of the temperature being in some, let's say, interval a? A is like from here to here. What is the probability of that happening? You look at the pre-image, all possible like events or states of the universe, such that for that particular event, the temperature of your room is in A. This is basically the pre-image of set A. Whatever is in here that is mapped to this interval. You start from A and you go and you color, let's say you say, oh, which part of my omega are mapped to this interval A. Now, what you have here is a probability measure. So if you have x inverse of A, this is what I have in yellow. This is x inverse of A. This is what is being mapped to A. You can ask, what is the measure of this set? This gives you a number between 0 and 1. Remember, the entire thing was omega, and the measure of omega was 1. And here I'm looking at a subset of omega, which is x inverse A. It's a subset of omega, so I get a number between 0 and 1. Okay, so this was the idea. Now, to sort of give you perspective and motivation, I'm using this maybe weird family of vertical subset. Now I'm going to use horizontal subsets as well. And I'm thinking that now you have two variables, x and y, and my two variables have, like, let's say one of them is temperature and the other one is some other parameter in the space. Okay, so now one thing that I want is that to think of x and y and think of them as they have their special sigma algebra. Remember, this was omega, and if you look at a particular interval here, you look at the x inverse of A, you would get a strip. Let's say this is here represented by this vertical yellow line. Now, and let's say no matter where you go and create like look at the subset here on the axis, and you look at the pre-image of that is vertical. What that tells you is that the sigma algebra, which is relevant to x, is actually a sigma algebra's vertical subsets. Okay, you can think of this example if I was sorting when I was labeling the events, I was using this axis to represent temperature. Then of course, if you say what are the states of my system that has this temperature in this interval, is going to be a vertical subset. Okay, and this other one is the other parameter. I don't know, like the like the time in the day or some other parameter in your environment. Okay, so you have two different parameters. Now, if you come here and if you look at the other parameter, then everything you take and you look at the pre-image is going to be horizontal. So here I have sigma algebra of vertical subsets, and here I have sigma algebra of horizontal subsets. Okay, so now the information, uh, random variable x and y, they come with their own sigma algebras. Now the idea why this is useful, so again we said this is for x we have vertical subset, for y we have. Okay, now let's say you have some information about x. You know that the value of the temperature is in this interval. And the question is that telling you anything about y? And you're assuming, of course, the omega is simple with the uniform probability across the square. And this is just for the illustration. But in this case, you see that having information about x, it doesn't tell you anything about y. If, for example, the pre-image was not a vertical strip, it was something like this. Okay, so if the pre-image was something like this, then you know if the temperature is in this interval, this is where you are in the event space. Now this is telling you, if you're looking at the y variable, let's say the y variable is electricity, and the x variable we said is a temperature. If you look at the y variable has higher probability around here, so it has higher probability in this specific range, and maybe less probability here. Okay, so having information about x in that case tells you something about y. But now in our case we have vertical subsets being the pre-image of the interval for x, and for any interval in the electricity we have a horizontal subset, and having information about one does not give you any useful information about the other. So now what that means, basically this translates into the fact that x and y are independent random variables. Okay, so in other words, the information about independence of x and y is encoded in their respective sigma algebras. And even more important, you see the information is in sigma algebra. It is not even related to how we label things. So like we take this point and we go right here. That is not relevant, because even before you label things, you have a sigma algebra for your random variable, and that sigma algebra can tell you if the two random variables defined in the same event space, if they are independent or not.